So almost, not almost, but the final module of the Cubes Camp course. Here we are. In the past week, um, you guys in the first module learned about the double slit experiment, which told you a little bit about quantum mechanics. And then we told you about classical computing because we wanted you to know a little bit of background. In order to appreciate quantum computers, it was necessary to understand a little bit better the classical computing. And then in the third or fourth module, we developed the mathematical background and the language that we would need to describe a lot of stuff in quantum mechanics and quantum computing, which then we moved out to talk about the fundamentals of quantum computing. What's a qubit? What are quantum gates? What are different types of single qubit quantum gates compared to classical computing? In quantum computing, you have much richer variety of quantum gates available and then in this seventh module, we discussed what are multi-qubit states, what are multi-qubit quantum gates. Then in the eighth module, we discussed Deutsches Algorithm. And in the ninth, that you just heard from Eric, we talked about quantum teleportation. So this was like very brief recap. And now I'd like to talk briefly about what was our motivation for this Cubes Camp. First, we wanted to give you a brief overview of what quantum computing is, sort of like a jump start where you could come in and appreciate how this is different than quantum, the normal classical computing. And the second was another really important reason was to get you excited, like to give you enough reasons to keep going and to like take quantum computing full time and hopefully like do it more in your undergrad, in your grad studies. And for that, what I'm gonna do is I'm going to discuss a little bit about the interpretations of quantum mechanics. So there are two popular interpretations of quantum mechanics, maybe a little bit more, but let's just discuss two. The first one is called the Copenhagen Interpretation, which follows the same picture that we provided you, where when we started talking about quantum mechanics, we just said, hey, these are the three rules, just the way you started with Newtonian mechanics, Newton's three laws. Just take these three axioms and run with them. But if you were to ask a little bit question, okay, how did we come up with the three axioms? What would the three axioms imply? Then there are like a lot of beautiful questions in them. So with Copenhagen interpretation, especially the last third axiom, at this point, I would have really liked sort of like a conversation approach, but we're on Zoom, so I'm just gonna assume that you guys provided me the third axiom of the measurement, where when you measure a quantum system, the wave function collapses to one of the states or one of the eigenfunctions. And the Copenhagen interpretation says, that's what happens. Don't ask me how, or don't go looking for deep answers. That's just the way it is. I'm not gonna go into any philosophical discussion with it. If you want to explain quantum systems, and if you want to engineer more interesting phenomenon, or you want to build more interesting quantum systems, these are the three rules. Don't ask me how, don't ask me where they, don't go into discussions about what they mean philosophically, but that's what these are. Whereas there's another very interesting interpretation, which is called many worlds interpretation. What that means is anytime you have a wave function, now wave function tells you um, there's possibility one, there's possibility two, and the actual wave function that describes the quantum systems tells you it could be also in a linear superposition of both of them. Now, what the many worlds interpretation tells you that it's not probabilistic, but it's actually there are multiple universes in which both those things happen. And this is sort of mind-blowing, where this was presented by Hugh Everett, where he said, you know what, the wave function collapse does not happen. What actually happens is when you measure it, you just go along one of the path in your universe. So if you had a qubit in 0 and 1 superposition, if let's say I can now were to measure it and I see 0, then what the many worlds interpretation says is that there must be another universe with a Kanab who measured 1. And this is really fascinating. David Deutsche, who came out with the first paper on quantum computation and whose algorithm you learned in this course, Deutsches algorithm. I'm gonna read out a couple of sentences from the abstract of his original paper, where he mentions that classical physics and the universal Turing machine, because the former is continuous and the later discrete, do not obey the principle, at least in the strong form above. A class of model computing machines, that is the quantum generalization of the class of Turing machines, is described, and it is shown that quantum theory and the universal quantum computer are compatible with the principle. And these do not include the computation of non-recursive functions, but they do include quantum parallelism, a method by which certain probabilistic tasks can be performed faster by a universal quantum computer than by any classical restrictions of it. And now comes the line that I want you guys to pay attention to. The intuitive explanation of these properties places an intolerable strain on all the interpretations of quantum theory other than the Everett's. And the Everett's interpretation is a many-world interpretation. So in his original paper, the reason he was interested in quantum computing was because he thought quantum computing sort of provided a proof of the many worlds interpretation. And why I'm mentioning this, because I know for a fact anyone who's remotely curious enough is going to find this fact that quantum computing as a proof of many worlds interpretation as something mind-blowing. I mean, it blows my mind all the time, where this is how the very small components could imply something really deep and fundamental. Just imagine there being like so many different universes. And so this is part of like the reason I wanted to give to you all, where there's something really fascinating in this field. So each of the modules that we covered are perhaps different multiple courses in universities where you're going to, like, there's a whole another major called computer science in universities that we just covered in module 2, right? So at some point you're gonna find all these things difficult, but the thing is, if you're interested in some really fundamental questions, which could affect our understanding of the universe, then this is sort of the field. This is something that may allow you to explore something fundamental. And then from that, I would like to quote two people, two of my favorite quotes. Curiosity demands that we ask questions, that we try to put things together and try to understand this multitude of aspects as perhaps resulting from the action of a relatively small number of elemental things and forces acting in an infinite variety of combinations. And another one is nothing in life is to be feared, it is only to be understood by none other than Marie Curie. And with that, I hopefully have motivated you. Now I'd like to describe three main classes of quantum algorithms, which are getting a lot of attention because they provide substantial amount of speed up over classical computers. So those three types are, the first one is the Shor's factoring algorithm, which depends on something that I mentioned in my previous talk, which is a quantum Fourier transform, which is a quantum analog of the discrete Fourier transform. The discrete Fourier transform could be implemented at best in order n log n steps, whereas quantum Fourier transform, okay, so when we, 33, we've got some interesting questions before we move on. So when we think of imaginary numbers, they're just values in another universe. I want to say no. It's no. Complex numbers. So there's inherently no reason to use complex numbers. It's just the reason we do it, you could have just used the normal real numbers, but then you would have had to use two separate numbers. And then what you would have had to say, hey, because these at some point are going to represent probabilities, there has to be some constraint among these two numbers. And turns out if you take appropriate constraints on those two real numbers, they just give you complex numbers. So that's like that's the whole reason. Otherwise, you can do all of quantum mechanics and all of quantum computation just using the normal real numbers. But what it implies is the linear superposition, where a particle could be in both two different states at the same time. That's where people argue that inherently means the presence of a separate universe, where if you measure it and you see something, you're in this universe, whereas there must be another universe where a different version of you measures the other possibility. Okay, when you mention, can you please zoom in a little? Oh, you mean, oh, sorry. Is that okay? Are we good? Celtic, new book there. And you said that, not Everett, David Deutsche. Just trying to understand. Yeah, so David Deutsche knew about Hugh Everett's interpretation, and in his universal quantum computation model, he argued that if, he didn't call it David Deutsche's algorithm, but he just said, like, the algorithm that I presented, if that works, that would sort of be a proof of like two separate universes. Okay, any more questions? Perfect. And so for the Shor's factoring algorithm, as I mentioned, it depends on quantum Fourier transform, which could implement the discrete Fourier transform in order log n square steps. Okay, and here's another catch, where what you do is you encode your information in the amplitudes. What that means is after Fourier transform, even though you've calculated Fourier transform for all the different amplitudes, you only get to measure one. So it's same sort of the stuff that we saw before, where even though you have calculation taking place on all the inputs, so if you got computational basis state, you can run the circuit. Another computational basis state, you can run the circuit. You've got a linear superposition, you can run the circuit, and the circuit would have ran on both the states at the same time. But when you finally measure it, you only get to see the one of the options. Okay, so quantum Fourier transform, it's the same caveat where it implements the transform really fast, but you only get to see only one of the amplitudes. So you got to do some more tweaks. And what Shor's algorithm addresses is the problem of factoring, where if you've got a random number, and let's say if I ask you what are the factors of that number, then turns out it's a difficult problem. I mean, if I ask you what are the factors of 15, it's easier for you to say, oh, it's just 3 and 5. But in general, if I give you a 9 or 10 digit number, then that becomes like a very difficult problem. And you could, so I have a very crude, unoptimized function written for it. And if you do that, you're going to see that the time to factor each consecutively big number, it just increases exponentially. So we've got, yeah, so I crash my kernel every time I run it. So let's see if I could run it with 5. What happened? There you go. Okay. Bottom line, you can try it on your own notebooks, and you can see that if you plot this function, and again, if you, oh, that was missing. So if I do it with 4, so turns out you could solve this same problem on a quantum computer much faster. And why is this important? Turns out this factoring problem is, it forms the backbone of a lot of the encryption used on internet. So all your credit card transactions and secure communication, at somewhere they're also looking for 2 really big prime numbers. So it has to do with the prime numbers. And if you could factor the numbers easily, then you could break the encryption. That might not have been a very good description, but I'm going to move on. In the next algorithm, which is very fascinating, is the quantum search algorithm. So in quantum factoring algorithm, the improvement was exponential, whereas in search, the improvement that you get is polynomial. What that means is in an unstructured search, so if I have a random element and I have, let's say, n different entries, and I'm looking for a particular entry, then in the worst case scenario, I may have to look through each of these entries to find the one that I'm looking for. And in the worst case scenario, it's easier to see that you may have to go through all the entries to find what you were looking for, okay? And in quantum, it turns out you could do it in order square root n steps, okay? And again, this may not seem a big improvement, but if you're Google, and if you could even have square root n, then that becomes like a huge factor, right? For example, if you were, if the improvement would translate directly into the cost, then it's easier to see that if you were spending, let's say, $1 million, now you could do it in just $1,000, right? So very rough translation, but if you could improve each of your search results by even polynomially, then you reduce the electric bill, which then translates to much lower cost. And then we come back to quantum simulation that I already talked about in my last talk, where the whole field of quantum computation owes its existence to Feynman, who was basically trying to solve the quantum simulation problem, where people were just interested in solving the Schrodinger equation. And he was the first one to flip the problem and say, hey, those things are already behaving quantum mechanically. Why don't you build a quantum computer out of them? Or why don't you build a controllable system out of them? And David Deutsche was also looking for thinking along the same lines, where he was, while approaching the problem of what functions can be calculated or what problems could be calculated using a computer, he argued that computers are physical systems, so we should start from a computer made from these quantum mechanical units, and then ask the question, what are the things we could compute, and then ask what is the efficiency we can do them with, right? And that sort of concludes the discussion, the last discussion of quantum algorithms. And again, recently, there have been many more quantum algorithms. People are exploring machine learning and a lot of other interesting things with quantum computers. And our hope is it's just going to, like, that the interest in the field is going to grow. But at the same time, we would also like to caution everyone to be very careful about what cannot be done on quantum computers and what can be done. Okay, so anytime you guys hear somebody claiming that quantum computers can check all the results or calculate all the different results at the same time, that's not how it works. So what we would like for everyone to do is just hone their skills, develop better understanding, and let us develop more interesting algorithms. At this point, does anyone have more questions? Okay. Beyond these, what are some other aspects that are currently in development? Yeah, so as I mentioned, there are like a couple of algorithms in machine learning, and then there's these variational quantum eigensolvers, which are sort of like a hybrid of classical and quantum computers. For example, as I mentioned, that the quantum systems are represented by 2 raised to power n vectors, and all the operations are represented by unitary matrix of size 2 raised to power n by 2 raised to power n. So what people have asked is, the quantum computers right now are very noisy. Is there a way we could just use their exponential Hilbert space and do optimization on classical computers? So basically, you're trying to get the best of both worlds and bring them together to solve interesting problems. So that's another very interesting class. Yeah, so VQE, and then there's been some interest in machine learning, and the quantum simulation itself, this is very broad. There are many more subcategories that you can explore. Quantum imaging and quantum sensing. So that is sort of not in the realm of quantum computing. That lies more in the realm of quantum mechanics and quantum engineering. So what we do in quantum algorithms is just take the abstract model of qubit and then say, hey, these are 0 and 1 states, just the way when you're using these classical computers, you don't ask, hey, how does the transistor works and so on. So it's similar to that. You have got your transistor, but similar technology could also be used to develop CCTVs and the CMOS camera in your phone, iPhone, and so on. Similarly, you use the quantum mechanical nature of those sensors to better image, develop better image. Because it's whatever sensor you've got, that depends on the intensity. But if the intensity is so low that you're just literally getting maybe a couple of photons every second or every minute, then you need to develop sensors which could basically detect a single photon. So I think, if I'm not completely wrong, then quantum imaging deals with quite a lot of that stuff where you're asking a lot of questions about the quantum mechanical nature of the device itself, so you could detect even a single photon. And for the sensing itself, you have these sensors, which again are quantum mechanical nature. How do they behave in different magnetic fields, different electric fields, right? So there's a good chance that you could use their properties to develop better sensors. Does that answer your question? Cool. And quantum algorithms and quantum computation, they start from, for example, you probably don't even need to know much of quantum mechanics in order to do quantum computation. As we just learned, like you could take very basics, few axioms of quantum mechanics, and then know how qubits behave, and then just go from there.